Okay, now we're going to look at properties of logarithms. Okay, so we're going to review a little bit first. We're going to talk about an exponential. So an exponential is when you have a base raised to an exponent. Like for example, 2 to the second power is a number raised to a number, but specifically an exponential looks like 3 raised to the x, or a number raised to an exponent, right? That's why we're calling it exponential, right? Because it's a function, so I have to have an x in there. And then we have a special kind of exponential, and that's this e here, which we use e for a lot of things. And e is about 2.718, blah, 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 blah. It's an irrational number. It's kind of like pi, right? So just know that a special type of exponential is e to the x, and e is a number. Remember that. It's just irrational, okay? A logarithm is the inverse of an exponential. So it is the opposite of an exponential. They cancel each other out, all right? And the way that we write a logarithm is log base b of x, where that b is a base, okay? So like we have base to an exponent here, we have log base b here, all right? And then a special type of logarithm is natural log, which I know it's weird that we don't do NL, we do LN, okay? But this is natural log of x. And guess what? The special exponential goes, with the special logarithm. So we'll see those going together. So our regular exponential goes with regular logarithm. Our special e goes with the special natural log. Okay, so it's kind of a very quick introduction. All right, so we're going to do a couple things with logarithms. First, we're going to switch back and forth. Okay, because they're exponential, because they're inverses, you can switch them back and forth. And so the way that we do it is what I call, we go around the world. Around the world. Okay, and back. Oops. Around the world and back. And the world is our equal sign. Okay, so you always start at the base for both types. So my base for number 1 is this 4. So I start at the 4. I go around the world, or around the equal sign, and then I come back. Okay, so around the world and back. Then the way I write it is this log base b of x. So we'll say log, and my base here is a 4. Right, and then this is where the going around the world comes in. I say of 16 equals x. So here's my base. I went around the world and I came back. And it's that setup every time we do this. Okay, so now here, well, let's do number 3. I should have done this in a different order. Start at the base, right? My base for a logarithm is a little number at the bottom, and then I go around the world and I come back, right? But now I'm writing it like an exponential. So my base is 2, and then I go around the world, and then equals coming back. So we're saying 2 to the 4th equals x. Okay, well now we got this e, my special exponential, and natural log, my special log. They go together, right? So that means that when I'm going to do the same thing. I start at my base e, and I go around the world, and I come back. But instead of using a log, I use natural log, because e and natural log go together. So instead of saying log base e, I'm just going to say natural log. And I don't have to put the base e, because they always go together. That's it. Natural log has to have base e. Right, so I'm going to say natural log, and then around the world, m equals back 2. So natural log of m equals 2. All right, and it looks kind of funny with the nm, but it's natural log of m equals 2. And then over here, I want to go start at my base, but there's nothing written there because it doesn't have to be written there. You automatically know, because it's natural log, that there's an e there that you don't have to write. Okay, then I go around the world and come back. So an exponential has a base to an exponent, and then it equals when you come back. So start at the base, go around the world, come back. Right? We can use that pattern to evaluate logs and sometimes solve if they're simple enough. So I kind of mix them up here, but these darkened circles are the ones that we're just going to evaluate. So I want to know what it equals. And then the other ones, I'm actually going to solve for x. All right, and we're going to do it by switching to an exponential, right? Because like up here, when I said log base 2 of x equals 4, I was able to switch it to an exponential, and I can do this in my head. right? I can do 2 to the 4th power to figure out what x is, but I would have no idea how to do log base 2 of x in my head, or equals 4, right? So I'm just going to switch it to an exponential, and it's going to make it a lot easier to figure out what I want. So for the first one, I start at my base, I go around the world, and I come back, right? So I have 2 to the 3rd power equals x. Well, 2 to the 3rd power is 8, so I know that 8 equals x. And that was super easy to do once I switched it to an exponential. Okay, for the second one, I just want to know what this equals. I want to evaluate log base 4 of 4. So what we're going to do is set it equal to x. Now I have an x that I'm solving for, right? But it's the same idea, because I want to take my base to an exponent and back. So I have 4 to the x equals 4. Okay, well, if I have 4 to a power has to equal 4 to, a power, right? This is 4 to the 1st power. That means that x has to equal 1. Okay, and that's actually a special case. Every time, make a little note up here, anytime I have a log of a base b of b, that could be 5 and 5 or 12 and 12, but anytime I have log of a base and then of the same base, it's always going to equal 1. Okay, so keep that in mind. It's one of our properties. Okay, then here for number 3, I have log of 100. I don't have a base written there, right? So for natural log, if there's no base, you automatically know that it's an e. It's always an e. For a log that doesn't have a base written there, it's what we call a common log, and it's a base of 10. So you don't have to write the 10, but if you don't see anything written there, that means it's going to be a 10 every single time. That's our common log, is base 10. And I could go into a whole long story about why it's 10, but I'm not going to, because we're just kind of getting the basics here. But I want to evaluate log base 10 of 100. So that is going to equal x, so that I can switch it to my exponential. So we can say 10 to the x equals 100, and I know that 10 squared equals 100, so that means x has to be 2. For number 4, I have that natural log, so that means that my base is e, even though it's not written there. So I'm going to start at my base, go around the world, come back. So I get that e squared equals x. So depending on what it wants, I could leave it as e squared, because that's correct, right? It just looks weird because it's not like a number. But remember, e is a irrational number like pi. But I could also type it in the calculator, right? And there's 2 ways to type it in the calculator. One is if you look above the division sign, there's an e. And also on the left-hand side, we've got a log and a natural log over here. And above the natural log, I have e to the x. Doesn't matter which one I do, so I'm going to do second divide, and then I'm going to raise it to the 2nd power. So I could say that this is also approximately 7.4. Okay, now pay attention. If you're asked to round on Delta Math, you have to round correctly, right? This one technically said 7.38, so if you put 7.3, you would get it wrong on Delta Math. So you got to make sure you round correctly and put 7.4. Okay, and then the last one, we've got natural log of 1. Okay, and again, I'm evaluating this one, so I'm going to go ahead and add in the equals x just so I can switch it. And then I have an e here that I don't have to write. Around the world, come back. So e to the x equals 1. Now, this one looks absolutely crazy, because how on earth is e to the x going to equal 1? You got to think back to our exponent rules. There's one special exponent where no matter what, if I have something raised to that number, it's always going to be 1. And that special exponent is 0. Anything raised to the 0 power is going to be 1. This is also one of our exponent rules, or our properties of logarithms. Okay, every time, if I have natural log of 1, it's going to equal 0. And if I have log of any base of 1, doesn't matter what your base is, if there's a 1 inside, it's going to be a 0. Okay, and then that same thing over here with natural log. If I have natural log of e, or ein, okay, that's base e of e, that's also going to equal 1. Okay, so it works for both log and natural log, and then same thing here. Okay, so that's 2 of our properties right there. But we got a couple more that we're going to look at. Okay, so for the properties, we have two main rules, and this goes across math in multiple areas. Like it works this way for our exponent rules, and you'll see it again later with other rules, all through different types of math. Okay, so addition is always going to go with multiplication, long word. Okay, subtraction always goes with division, and vice versa. Okay, so remember that. And then we also have a power property. The power property says that if I have a log of something raised to a power, if I have an exponent inside the logarithm, I can move that exponent out front. So this would be the same as 2 times log base b of x. So those are our three main properties. Okay, that addition goes with multiplication, subtraction with division, and vice versa. And then the exponents can go out in front. The reason we need to know this is because you will be asked to expand and condense logarithms. So expand is to get bigger. So that means I'm going to take this log and I'm going to give everything inside its own logarithm. Condensing means I take all the logs and push them together to make one. Okay, so if I start with log base b of xy squared, this is kind of like a rule that we're writing here since I'm using all variables. Inside my logarithm, I have multiplication. I have x times y squared. Well, multiplication goes with addition. Okay, so that means I can break this apart by saying log base b of x plus log base b of y squared. All right, they keep the same beginning part. That doesn't go away. That's going to stay with these guys the entire time. Right, and then there's one more thing I can do. If I have an exponent, I'm going to move it out in front. Now, only the y has this exponent, so that means it only goes in front of the log that has a y in it. So then this ends up being log base b of x plus 2 log base b of y. And that's my expanded form. That's as far as we can go. All right, the second one, same rules apply, it's just natural log instead of log. So the x's and the y's are going to keep a natural log with it. Okay, subtraction and division go together. So I have top divided by bottom. So that's going to be top minus bottom. So this ends up being natural log of x minus natural log of y. So if you have multiplication, you can break it apart using addition. If you have division, you can break it apart using subtraction. Okay. Condensing is the opposite of expanding, pushing it together. So I have a subtraction here. Subtraction goes to division. So that means I'm going to have the first one divided by the second one. So this one's going to end up being log base b of m divided by p. Okay, now the parentheses aren't really that important here. Like you could use the parentheses there or you can leave it as an m. Doesn't matter. I could leave this as m over p or I could put it in parentheses. Doesn't matter as long as it's one term in there. All right, and then for the second one, before I add, I got to take care of any numbers out in front because this has to be the same. Like I have log base b, so I can combine those. But here I have 2 natural log and natural log. They're not the same, can't push them together yet. So what we do is we're going to take this number out front, put it back inside as an exponent. So we're doing the opposite of putting the exponent out in front. So then this is going to be natural log of a squared plus natural log of b, right? And then addition goes with multiplication. So I have the first one times the second one. So we have natural log of a squared times b. Okay, so that's kind of a generic way of looking at it with all of the variables. Now we got some examples to do with actual numbers in there. Okay, so let me get centered here. The first set we're going to expand. Okay, and I'm actually going to kind of go out of order a little bit because I want to save that one. I don't know why I put it first. Okay, but I'm going to start with the second one. So overall I have multiplication, but I do have 3 pieces in here, 3 different things, x and a y and a z. So that means I'm going to have 3 different logarithms. Okay, so I'm going to start by breaking them up. I'm going to give all of these guys their own log. So I have log base 3 of x squared. Okay, and I'm multiplying, so that translates to adding. And then I have log base 3 of y cubed plus log base 3 of z. This guy's done. Nothing's going to happen to him, but both of these have exponents. So my exponents have to pop out front. So then I'm going to end up with 2 log base 3 of x plus 3 log base 3 of y plus log base 3 of z, and that's as far as we can go. So multiplication becomes adding, exponents go out in front, done. Okay, for the next one, there's two ways of looking at it. So first, the way that I usually do it is because my exponent's on the outside of the parentheses, I'm going to go ahead and move it out in front. So I'm going to have 2 times natural log of x divided by y. Or, if you wanted to, you could go ahead and distribute it to top and bottom. So you could make that an x squared over a y squared. You'll get to the same answer at the end, but it'll look a little bit different. Okay, so now this 2 times natural log has to stay with both the x and the y because it's in front of them when they're both inside. So that means that when I break this apart to do subtraction, I'm going to have 2 natural log x minus 2 natural log y. Okay, because they both were raised to the second power, the 2 goes out in front of both of them. All right, and then back to this first one over here. Okay, I technically have multiplication and division all in the same problem, right? Because I have x times y, and then I have that divided by z. Okay, so what I'm going to do is look at the big picture first. My big picture is division because I have a top divided by a bottom. So I'm going to go with subtraction. So I'm going to do the top minus the bottom. So I have log base 4 of the top, xy, minus log base 4 of the bottom, z. Okay, now log base 4 of z, done. There's nothing else I can do to simplify that. Log base 4 of xy, though, has multiplication, which is going to turn into addition. So I have log base 4 of the first one, x, plus log base 4 of the second one, y, and then bring down my minus log base 4 of z. And then our last three we're going to condense. So we're going to take all these logs and push them together to have one single log. But you got to double check, make sure that it's the same log. So I have log base 3, we're good there. Here I have natural log, natural log, natural log, and then my common log, so log base 10, and then common log, log base 10. So I'm good there. I don't have anything wonky. So we're just going to start combining them using our rules. The first thing I do is always get rid of the numbers out in front. So I'm going to go ahead and put this back in and put that back in. So this is log base 3 of x to the 6th plus log base 3 of y to the 6th. And then addition goes with multiplication. So I have log base 3 of x to the 6th, y to the 6th. Okay, now another way of thinking about it, which I don't know why I do them kind of opposite, but because they both have a 6 out in front, I could change colors. I could have already combined them because this whole part's the same and then this whole part's the same. So I could have said this is 6 log base 3 of xy. Then put this out in front, but if I do it that way, this exponent goes to the whole thing, not just the y, so you do have to make sure that you put it in parentheses. These are the same thing, right? It's just this one's if I distributed the 6 there. Okay, so either way is fine. Just make sure you keep your, your writing the correct way, the way that you write everything out. Okay, now for number 2, I can't do it this way in red because this one doesn't have a number and then I have a 3 and a 2. They don't all have the same number. So the first thing I'm going to do is get rid of those numbers out in front. All right, and then work left to right. So start from the beginning. Okay, so I'm going to start with these two first, and we'll come back and add the z in later. So the first thing I come across is plus. That means I'm going to be multiplying. So I'm going to have natural log of x times y cubed minus natural log of z squared. Now I have subtraction, which goes with division. So I have the first one divided by the second one. And that's it. And for the third one, First thing I do is put my exponents back in. They're different, so I can't go ahead and do like what we did over here. So I have log of x cubed minus log of y cubed. Subtraction goes with division. So I have log of x cubed divided by y cubed. Nope. This is a 4. I was about to say. I don't know what I was thinking. So x cubed divided by y to the 4th. Okay, so multiplication goes with addition, division goes with subtraction, and exponents can go out in front.